Hello, everyone. I'm Sumayah. As you heard in my introduction, I am Director of Data Science at Cedar. And if you haven't heard of Cedar, we're working on building the best healthcare financial engagement platform for patients. And one of the features that my team worked on is ML-powered discounts. And we're working to improve financial outcomes for both patients and providers. So today I'll be telling you about ML-powered discounts, but before I go into the details on that, I'll tell you a little bit more about the problem we're trying to solve. So, long story short, patients and providers are both struggling. I think anyone who lives here in the United States knows that affording healthcare is a huge challenge for many, many Americans. 1 in 6 Americans have had a medical bill go into collections. And a recent survey has shown that 40% of people have avoided getting medical care due to the cost. And this is just extremely sad. And then on the other side of the story, providers are struggling as well. So providers can be health systems like hospitals, doctors' offices. And for them, financial pressures are at an all-time high and are getting worse. So inflation is driving up costs, staffing shortages are straining labor-intensive activities like revenue cycle management, and in some areas, patient volumes still haven't returned to pre-pandemic levels. So for all these reasons, they're facing financial pressures as well. So at Cedar, our mission is to empower us all to easily and affordably pursue the care that we need. And to go into more details on how we do this, we kind of have multiple parts to our platform. So we have Cedar Pre, which is a pre-visit experience, so that helps patients check in for their visit. And then we have Cedar Pay, which is a post-visit billing platform. So the feature that I'll be telling you about today is part of Cedar Pay. So essentially, the main idea here is discounts, reducing the amount of a person's bill to help encourage that person to pay. So the question that we're trying to answer is, can we use discounts to increase collection rates for self-pay patients? And self-pay patients are those without insurance, so they're the population that's eligible for discounts. And as you can imagine, these patients have a very hard time affording their bills. So if we can give them a discount to help them out, that would be something that would be super impactful to our mission. So to start on this work, we ran an initial experiment. So we tested out different discount sizes. No discount, 15%, 30%, and 45%. And we also played with a few other variables. For example, discount expiration. So that's whether a discount expires after a certain amount of time, such as 30 days, or is the discount available for the entire period that the patient has to pay their bill, which in this case is 120 days. Next, another variable is discount application. So is the discount only able to be applied to the whole bill? For example, does the patient have to pay the whole bill at once to get that 30% discount? Or can the discount be combined with a payment plan? So that's another thing we tested out. And then for the discounts that can be applied to payment plans, what is the best max payment plan duration? For example, should the payment plan length go up to 6 months or 12 months? With 12 months, of course, having smaller monthly payments that spread out over a longer period of time. So we launched an experiment a couple years ago where we were testing out all of these variables. And we saw some really interesting results. So our first and most important finding is that discounts need to be combined with payment plans in order to be effective. If we limit it to the total amount, it still wasn't effective enough at bringing down the bill to an amount that was affordable for the patient. The patient needed the flexibility of breaking it into those smaller monthly payment options. We also found that discounts that expire perform better. So if we tell the patient you have to use this discount within 30 days or then it's gone, that creates more of a sense of urgency and the patient is encouraged to actually pay their bill. And then when we compared the different discount rates, what we actually saw is that the 15% discount variant performed the best. So what this graph is showing is collection rates. So that's out of the total amount of the original bill, how many dollars or what percent was actually collected, what percent did the patient pay. And what we saw is that by giving a 15% discount, and everyone in this experiment group received that 15% discount, by giving the 15% discount to everyone, we actually created a 0.5% absolute increase in collections rate compared to no discount. And this is a very meaningful increase at the scale we're talking about. So that was our initial experiment where we tested out these discount levels where everyone in the experiment group got the same discount. And then our next question is, can we do even better with ML? Can we use ML to intelligently determine for each patient, should they get a discount? And if so, how much should that discount be? So there are many potential ways that we could approach this problem, but I'll tell you about the approach that we took. And I'll start off by just kind of explaining how we built the model. So we had collected data over the course of over a year, and we had all of this historical data of patients in these different discount experiment groups. And we had the collections results for those patients. We were able to see which of the patients paid and which did not. And of course, we had all of the patient visit details and bill details. So using this historical data, we were able to train a model that took in the discount percentage or discount amount as a feature and was able to use that information combined with the patient details to predict the likelihood of payment. So now that we had this model, we could apply it to any new patients that were coming in. We ran the model 4 times for each patient, 1 time with each of the discount levels, and got a predicted payment likelihood for each of these discount levels. And the target variable that we used in the prediction is whether or not that person paid in that 120-day period. So paid could mean paying in whole or starting a payment plan. So we were able to get the predicted likelihood of payment. Then what we did with this predicted likelihood is combine it with the discounted amount. So for example, if the original amount of the bill was $1,000 with a 30% discount, that would be $700. So by combining the predicted likelihood of payment with the discounted amount, we could calculate an expected value. So by getting the expected value for each of the different possible discounts, we could identify which expected value was the highest and would thus lead to the highest predicted collections for that patient and give them that discount. So for this particular example, the 30% discount was best. So that was our approach for our V1 of ML-powered discounts. So this was an XGBoost classifier that we built. It predicted the likelihood of payment using a number of features, including the discount size. And when we tested this model offline on our test set, what we saw is that the model seemed to be performing extremely well. The predicted payment likelihood was extremely accurate. Our model's calibration curves looked great. And things were looking good. But when we launched it to a live patient population as part of a new experiment group that we added to our experiment, what we saw is that the model actually performed very poorly. It led to the lowest collection rate of any group. And another interesting thing is it actually only led to a discount being given 12% of the time. And this actually could have been a sign that maybe we wouldn't get the best results, because we had seen in our first round of experiment that the 15% discount, where we gave 15% to everyone, worked best. And this model was barely giving discounts at all. So digging into the data a little bit further, we saw some interesting things. So you might remember that the target variable that we were trying to predict was the likelihood of payment in 120 days. But the thing about that target variable, it was actually extremely similar between the different discount levels. For example, maybe like 10% of people with a 0% discount paid, and 10.1% of people with a 15% discount paid. So although the discount had an impact, the impact was small compared to all the other things that influenced likelihood of payment. So because there were other things that influenced likelihood of payment much more, the model was, the discount size was sort of getting overshadowed by these other features. So if we were to look at the predictions that the model made in one sample patient scenario, we can see that for 0% discount, and this is just for one patient, we can see if we gave this patient a 0% discount, it's a 28% probability. And then the model says if you give them 15%, it actually goes down. And then goes up again for 30% and then goes down for 45%. And this actually makes no sense at all. It does not seem reasonable that giving a person a very large discount would decrease their likelihood to pay. If anything, it would be the same or more. So we sort of saw these signals that our model was behaving strangely, and we wanted to think of some strategies to try to provide the model and provide our approach with the data that it needed in order to make more rational decisions. So one thing that we saw when we went back and analyzed our historical data is that discounts actually influences collections beyond the first 120 days. You might be wondering how that could be, because 120 days is actually the deadline for the patient to pay or to set up their payment plan. But what we saw is that payment plans on smaller sized bills are actually more likely to be completed. So for example, if we discounted a bill from $1,000 to then $700, even if in both situations the patient started a payment plan on the amount, they were actually more likely to finish out that payment plan and not break it if it was a $700 bill and not the $1,000 bill. So this chart is kind of showing that trend. Here is the amount that's collected given that the person pays or starts a plan. So I kind of call that the recovery rate. And as you can see, as the amount billed gets larger, the amount we can expect to recover goes down. And since in our target variable, we were just looking at payment in the first 120 days, so we did not account for this trend at all. And our logic or our approach did not really take into account the positive impact of the discounts by bringing down the size of the bill and making it more likely for a person to complete their plan. And this is one of the reasons that the model was very rarely giving discounts at all. So going back to our original approach, we had these two steps where we predict the likelihood of payment and then use that likelihood of payment to calculate an expected value. So of course, the predicted payment likelihood is that payment in the first 120 days. But if we add an additional step where we apply an adjustment to account for payment plan defaults, this is something that can then influence the expected value calculation and actually leads to more discounts because we're seeing and we're capturing the value, the long-term value of bringing down the size of the bill. So with this updated approach, this led to more patients being helped with discounts. The model was now giving a majority of people a 15% discount. And this is definitely great for us because it helps with our mission to increase affordability for as many patients as we can. And what we're also hoping is that it will lead to better collections rates, so better results for providers. So this was actually just one of the improvements we made to the model. There are a couple other things we worked on relating to the feature set and our architecture and the way our model and experiment was set up. So we made these improvements, including emphasizing the benefit that comes from having a smaller bill in the long term. And we launched an updated ML model. So we tested this model alongside our other experiment groups, which were the no discount, 15%, 30%, and 45%. And the other groups, like the same discount was being given to everyone. So we launched this late last year. And we don't have final results yet because the outcome variable that we look at is, of course, the payment in the first 120 days. So we haven't completed that cycle yet. And of course, the longer-term outcomes, like the payment plan completion, are already very exciting, or are also very exciting to us. But I do have some very early results. So looking at these plots are showing the collections rate performance of the different groups. So going from top to bottom, it's the ML model, 15% discount, 30%, 45%. And on the left is our ML-V1. On the right is the updated ML model. And as you can see in V1, as I alluded to earlier, it was the worst performing of all the options. But looking at our updated model, it is looking pretty good. It looks to be on par with our 15% and 30% experiment arms. But of course, we don't want it to be on par. We want it to be even better because it seems to make sense that by determining for each individual patient what discount they should receive, that should lead to better results than just giving the same discount for everyone. So it seems like we're not quite there yet with our ML. And something might still be missing, despite these big improvements that we made. So what might be missing? Well, what I want to think about now are the changing economic conditions across time. So ignoring the ML model result for a second, let's just look at the different discount experiment arms. Looking at the early 2022 data, we see that the 15% discount arm is performing best. But if we looked at more recent data from the past few months, we actually see that the 30% discount performs best. One potential reason for why this might be is because economic conditions have changed quite a bit from early 2022 to now. The economy was much stronger then, the inflation rate is higher now, people are struggling more now to afford their bills. So this could be a reason why that larger discount is needed to really make the bill affordable for the patient and to convince the patient to pay their bill. So because of these changing economic conditions, we can understand why our model, which was trained on this earlier data, might not be performing the best now, because we saw that our model is actually giving mostly 15% discount. So it's a bit behind the times because the 15% discount was performing best early last year, not necessarily right now. So an ideal model would be trained on more recent data, and it would account for changing economic conditions. So it's not enough just to try to train it on just more recent data. For example, if we were to try to just say, okay, let's look at the last week and build a model just based off of that, that wouldn't be possible because we don't have any outcomes for those patients quite yet. We do have to utilize older data since we're waiting for those 120 days to pass to get the outcome. But there might be ways that we can still account for the changing economic conditions. One way that we could do that is by adding a feature that represents the economic conditions at the time. So for example, one feature that we have in mind is the rate of payment plan defaults or cancellations for that patient population. So as you can imagine, in more challenging economic times, more and more people are likely to default on their bill. They don't have enough money in their account that month to make their payment, and they default on their plan. So if we look at the rate of defaults, that could be a signal as to how our patient population is doing at that particular point in time. So that's one thing we want to do. Another area that we really want to explore is to better understand the impact of plan length. So now that we're in a more non-zero interest rate environment, what really matters to providers is also not just how much they can collect, but time to collect as well. It's beneficial to the provider if more patients sign up for the 6-month plan and the provider gets fully paid within the 6 months versus the 12-month plan where it takes longer to get paid. So that's something we can dig into more and understand how these plan lengths interact with discounts and analyze the value of getting the collection sooner and work that into the way we're modeling the problem. And there are several other ideas we have that I won't get into here, but this was a really interesting project to work on. And I think my big takeaway that I want to emphasize here is that like in many ML projects, I think we heard about it a little bit this morning too, sometimes it's easy to focus on the short-term outcome and model a problem in that way. But in order to really build a robust solution that works in the long term, it's important to look at long-term outcomes and to make sure that those are being incorporated into the approach, and the system that you're building is really intended to maximize and optimize for those long-term patterns and effects. So yeah, that's one main takeaway. And I think another really exciting part, which we haven't explored yet, but hope to, is that sometimes it's not just information about what you have on hand in that system, or in our case, for that patient, for their bill, for their visit details. It could also be about the bigger picture, the overall conditions of the world, and making sure to work that in as well. And that's where our feature that will represent the economic conditions will come in. So that is just one example of how we use data science at Cedar to help both patients and providers. I encourage you to look us up online. We have a couple of different blogs. One is the Patient Experience Studio, which is our data science and design blog. And then we have our Tech Decode blog, which is our engineering blog. So yeah, at this point, I will take questions from anyone.
Hello. Hello, thanks for a great presentation. In your context, how do you measure moral hazard, and what are some ways that your algorithm guards against that? So say, for example, customers know that if they're delinquent in their payments, that they're going to get a discount, and you have people who previously would have paid on time now kind of hedging their bets. If you can talk a little bit about ways in which people might try to game the system and how you might counteract that.
Yeah, that's a great question. So the way we structured the problem at first is by entering patients into one of the experiment arms. So that would be like the 0%, 15%, or ML arm, and then keeping them in that group for as long as they were a patient at Cedar. So once they received that particular discount, they were kept in the discount group, and their discount amount didn't change. So people who were in the no discount group had no idea that these discounts were happening, and people who were in the discount group always got a discount. However, we had to change this because we realized that this setup did not work very well for ML. With this setup, the model was not being exposed to any repeat patients because a person was just getting looped into one group, and then we were never assigning them to a different group. So that was an issue. So we reframed our system so that a person was in their particular experiment group throughout the duration of their billing cycle. So if they got more bills while that first bill was still open, the same discount was applied. However, if they closed out that bill and then got a new discount or got a new bill, they would then be re-entered into the experiment and could get any of the discount options. So if in that case, the person who previously got a discount then got 0% discount, of course they might be a little disappointed. But the way we tried to address that is we didn't give any delayed discounts. What happened with the discount is as soon as we assigned the bill to the patient, the discount was applied immediately and then expired within 30 days. So there wasn't really a scenario of the patient's like, okay, maybe discount would get added later. If they had received the discount before, they knew it comes at the very beginning. If it didn't come at the beginning, it's not coming at all. So I guess that's one way we kind of address that issue of people trying to kind of hedge their bets in that way. But yeah, overall, I think that's, still going to be something that we always think about, and it definitely is a problem that is faced not only with discounts, but like other aspects of our product. Like, for example, there are people who set up payment plans and then figure out that they can kind of keep extending the length of their plan and never quite finish. So there are always going to be people who try to game the system, but that's a very, very small minority of patients, and we're trying to solve problems for the vast majority who aren't gaming the system, and I think in many ways we are going to accept that it won't work perfectly, and we'll have to do the best we can with the strategies that I mentioned.
Hi, thank you for the presentation. I have a question about the engagement history data that you mentioned on the slides. How do you make sure that the features are chosen in a fair way in terms of, is that engagement history based on how they paid the bills or based on their capability to pay the bill? If you can explain a little bit on that.
Yeah, so for the engagement history, we looked at a variety of features. Some of the features had to do with the way they interacted with the Cedar product, what sort of information they gave to us. For example, did they provide an email address as contact information or a phone number? So we had all of these examples of information that the patient provided to us and the ways that they interacted with our app. One thing that we did not include in our model is any demographic features. So we, at least with our initial models, we wanted to really play it safe and make sure that we were kind of including features that wouldn't create any sort of bias. So we're really trying to anticipate, from what we know about the patient, which is like the information that they provide to us, the way they interact with our app, how likely they are to pay. So yeah, those are the features that we looked at.
Does their just economic situation count into that? That they're like personal ability to pay? Because some people would pay but won't buy groceries, right? So how does that factor in?
That's a great question. So we didn't factor the person's ability to pay in this model. One idea we have on how to do that is by trying to get a sense of their income level by looking at the median income for the zip code that they live in. So patients who live in lower income zip codes are less likely to be able to have the means to pay and are more likely to have a harder time affording their bill. So in future iterations of the model, if we were to incorporate such a feature like median income for the zip code, we would want to ensure that we're giving more discounts to the areas that have lower median incomes to help those patients that are disadvantaged.
Thank you. Thanks.
I have a question regarding how a previous discount would influence another one. So for example, if a patient received a 30% discount, but then later received a lower discount, or the reverse, received a lower discount first and then a higher discount later. So have you researched on how that would impact their behavior in payment?
I think that's a great question, but no, I haven't researched that yet. So we actually only made this change. So yeah, that very one on the right side, ensuring that the ML model is exposed to repeat patients. We just made that change late last year. So we don't have too much data quite yet where a person gets one discount first and then at a different billing cycle gets another discount later. But that is something that we want to look at and analyze. And just based off what I'd guess, purely just from my own thoughts, I can imagine someone being not too happy that they got a larger discount and then no discount at all or a smaller discount. And that's actually why originally we had the plan of like get one discount and then stick with it because we thought of that situation. But it really didn't enable us to leverage the value that we wanted from the ML, so we had to change it. But I think that is something that will be very interesting to see when we do look at those results. Thank you.
Hello. That was a great presentation, as well as it's a very interesting topic. I always think about if my doctor gave me 30% discount, would I go to him more often? Probably not, because he never gives me a good, like a good information. He always gives me a bad information or a bad result. So my question to you is, have you looked at the data, like have you looked at the discount level of 90% to 100% discount? Just because the people who don't have insurance, they don't make a lot of money. If the bill is $1,000, it's still a very, even if they pay $700, it's a very big amount. It's better to avoid going to the doctor than paying $700 sometimes. So have you looked at the numbers, or have you contacted the doctors or even the patient and figured out a way to discount it even further than just 30% or 45%?
That's a great question. So with the work that we're doing now, the largest discount that we experimented with was the 45% discount. And what we saw with the 45% discount is that even though it encouraged more people to pay their bill, it still led to lower overall collection rates because the discount was so large that even though it encouraged more people to pay, the dollars received by the provider was ultimately less compared to the 30% or 15% discount. So with the way that we're attempting to solve the problem now by applying the discount with the ultimate goal to increase collection rates for the provider, a 90% discount wouldn't be feasible because it would discount the bill so much that the provider wouldn't benefit. However, I agree completely with you that there are so many people out there who, with a 30% discount or even 45% discount, that doesn't make a dent. They couldn't afford their bill before. They still can't afford their bill now, and that's not going to help them. So what we're doing at Cedar now is working to connect these patients with financial assistance options. So there might be patients out there who are not aware of certain things like government-funded programs, charity care, and these different organizations that partner with these providers and try to help patients who are just unable to pay their bills and cover it in that way. And with that approach, the provider gets paid from somewhere because they ultimately have to make revenue in order to keep functioning because these hospitals are for the most part a business. So that gets the provider paid, but it also helps these patients who have these large bills, like $1,000. Many people can't afford half of that. So we are working in other ways to solve those problems for those patients.
Unfortunately, time is already up, even though I'm sure there are more questions. Thank you so much, Sumayah, for that great presentation. Big applause for her. That was really good.